We're glad to have Eun-Ah Kim from Cornell University today, and she'll tell us about fractionalization in fractional correlated insulators.
Well, thank you for the invitation. Very happy to be here. I want to talk about fractionalization in fractional correlated insulator. I will have to define what I mean by fractional correlated insulator in the context of twisted Moray systems, twisted bilayer Moray systems. But before I start, I want to invite people to ask questions, interrupt me, and ask questions along the way rather than waiting until the end. Okay, so all right, so let me start by acknowledging my collaborators. This work was led by my student Kevin Zhang and Beire Kick Fellow postdoc Dan Mao. And in the early stages of work, the first paper on the subject, we had a pleasure of collaborating with Yang Zhang, who was a postdoc at MIT. He's now moving on as a faculty himself, and Liang Fu. You can find details of the first paper in this preprint, which will be available, which will appear in a journal very soon. And the second part, perhaps the newer part, is the exciting newer part is in preparation. So fractionalization. We think of fractionalization as perhaps the most dramatic and consequential effect of a result of interaction. And we have the study of fractionalization started with study of fractional quantum Hall effect, and the successes in understanding fractional quantum Hall effect, especially using conformal field theory, I guess the theme of this conference, is one of the greatest triumphs of theory. Now, in for fractional quantum Hall effect, we take kinetic energy and interaction that is in any Hamiltonian, and we approach it from one limit. Because magnetic field quenches the kinetic energy, you have Landau levels, and you consider the limit where the Landau level mixing can be ignored. You can just really ignore kinetic energy altogether and just focus on the interaction. And that's why small systems can, exact diagonalization studies of small systems yield very accurate results, because you don't really have to face the frustration between kinetic energy and interaction phase up front, because you just have quenched the kinetic energy. And this is the starting with the quenched kinetic energy and considering interactions that are projected to that level is a familiar route of fractional quantum Hall effect leading to fractionalization. Now, one can consider starting from the other limit, the limit of starting from strong interaction, instead of starting from kinetic energy and then quenching it. We can start from strong interaction, and that's a strong coupling limit. And in the strong coupling limit, with any finite range interaction, you're going to get a crystalline phase. And you can ask whether by melting the crystalline phase, one can get a non-trivial fractional state. So a strong coupling limit would be a Wigner crystal-like state, and we can ask whether a non-trivial effect can occur, especially in the with fractionalization, starting from that perspective. Now, what you'll be doing is to start with a crystalline state and try to melt it with quantum fluctuation. Now, this program is very difficult, and studying the classical limit is readily possible. You can study it if you don't have any other means. You can just study it with classical Monte Carlo. But adding quantum fluctuation is generally very difficult. And to know with confidence that you're getting a fractionalized state is challenging. But this is the angle that we are taking, and we are daring to take this angle because we have a new platform that gives us a lot of, get us up pretty far with some simple geometric considerations. So that new platform is twisted bilayer graphene Moray systems. You probably have heard a lot about twisted bilayer Moray, but the efforts in the community up to now have generally focused on integer fillings for good reason. Even if it weren't for experiments, integer fillings are obviously a good place to start. You would want to start understanding integer filling. At least that's how fractional quantum Hall effect progressed. But more importantly, from the very early discovery of twisted bilayer graphene, it was integer fillings that showed insulating states, which must be due to correlation. And at the edges of those insulating states, superconductivity was discovered. So a lot of effort and a lot of went into understanding integer filling, and quite a bit of progress has been made and new insights have been gained. However, little attention has been given to fractional filling, and I want to draw attention to fractional filling. Why did no one pay a lot of attention to fractional filling? Little attention was given to fractional filling because whether you look at twisted bilayer, when you look at twisted bilayer graphene, when you change the filling through some fractional filling, you find very little changes. So on the left-hand side is, this is a familiar, take your two honeycomb lattice and twist it picture. And when you twist it, twist the two bilayer, you have a triangular lattice of AA sites. So these are the AA sites where the two layers are really commensurate. And then there are AB and BA sites where they are maximally misaligned. Now, these AAs, the AA sites show strongest intensity when you look at the system with STM. So, and when you look at the system with bare eyes, well, system here being PowerPoint, you also see strongest intensity at AA sites, which form triangular lattice. So initial thoughts about, very early day thoughts about twisted bilayer focused on the triangular lattice. Experimentally, practically, when you look at the system, you see these triangular lattice, and you go through changes of filling in between integers, and you see very little change. It stays the same. Therefore, there wasn't a major motivator to look at fractional filling experimentally. This is in huge contrast to another Moray system, TMD-based Moray system, twisted transition metal dichalcogenide. Here, this is an STM experiment on transition metal dichalcogenide TMD Moray system. And what they find is that integer filling, every side of a triangular lattice is occupied. And at 1/3 filling, only 1/3 of them are occupied, showing enlargement of the unit cell at 1/3 filling compared to integer filling. So this is a this is a picture that makes a lot of sense. That you have further range interaction and you lower the filling, you're going to form an array, sort of like Wigner crystal put on a lattice. But that's not what is observed in twisted bilayer graphene. And because little change was noticeable upon changing the filling, there had not been a lot of thought going into fractional filling. However, there were some hints indicating perhaps there is something going on at fractional filling. This is a very early, this is a paper from Pablo's group last year. where they reported, where they are reporting the effect on magnetic field effect on a superconducting dome. At zero field, first thing you can notice, I think this is a screen capture from Pablo's talk, and he put the arrow here, which is not in the paper. You see a dip in superconducting dome. So that's a dip. And that dip is very reminiscent of suppression of superconductivity at 1/8 filling in high DC cuprates, so-called 1/8 anomaly. Furthermore, when you take this dome and apply magnetic field, which suppresses superconductivity, what shows up in this region where that dip is upon suppression of superconductivity is insulating state. More recently, this is towards the end of last year. This was early last year. This is towards the end of last year. Harvard MIT collaboration have reported fractional churn insulating states, but this is a figure from that paper where you see incompressible state at a filling related to 1/3 without a slope that is magnetic field independent. So when there's a slope like here, that shows it is a churn insulating state which breaks time reversal symmetry. But when there is no slope, this is churn number 0 incompressible state. This paper came after our preprint proposing some new ideas, theoretical ideas about incompressible state, possibility of incompressible state at fillings related to 1/3, which in our thinking was motivated by these observations and theoretical considerations. Now, we believe this is data from Harvard MIT collaboration that is published. This is unpublished data from Jeannie Lau and Mark Baccarat at OSU. And both of these experiments are finding incompressible states at integer plus minus 1/3. So now these experiments finally motivate us to think about integer plus minus 1/3 state. So why is TBG so different from TMD?
I have a question.
Yes?
Just the previous slide, the right panel, the TBG, what's the filling?
This one, oh yeah, this one was either 1/3 or 11/3. I don't remember exactly. Oh, no, you know what? Actually, no, the filling's shown here, back here. These are the filling. So horizontal axis is back A. That's changing the charge density. So this incompressible state here is, so this is near one. So this experiment was at magic angle. This is not at magic angle, 1.3. That's somewhat away from magic angle. And you have incompressible state at integer filling, but this is 1/3, that is minus 1/3, that is very prominent. Does that answer your question?
Yeah. And how about the 4/3?
Yeah, 4/3 is also showing, yeah, that's not as strong as 1/3, but both are related to integer plus 1/3, plus minus 1/3.
Okay, good. Thanks.
Yeah, good. All right. Thank you. Okay, so I said earlier that TBG morae and TMD morae are quite different when you want to start thinking about fractional filling. So now let's look at why it is different. It's about whether you can what does the local description, position basis description of your model look like. That's where the difference is. When you linearize, when you look for linearization of TMD morae systems, they form nicely localized orbitals centered at the AA sites. However, when you look at the linearization of TBG, although when you the STM data look like you've got nicely localized blobs of density of states at AA sites forming triangular lattice, It's been shown by several different groups, almost at the same time, that you cannot, your van der orbital is not going to be localized just at one of these sites, but rather you have to really think of it as van der orbital centered at the center of the triangle, that is the AB or BA site, with the weight spread on 3 nearby AA sites. So the reason is, if you try to form localized van der orbitals on a triangular lattice, you cannot recover the fact that your individual graphene layer came from honeycomb lattice. You don't get the correct symmetry. And you can think about this issue from the valley churn number perspective, or you can think about it from the perspective of point group symmetry. Either way, when you try to form maximally localized van der orbitals, what you find is that you really want to work with the basis on the honeycomb lattice. So centers of the triangles form a honeycomb lattice, and that's why that basis makes the preserves the symmetry. And but the weight of the wave functions are on these 3 AA BB sites. So these 3 groups arrived at all same conclusion, that your van der orbital, the most you can localize is going to be to center the electron wave function at BA or AB site, but distribute that electron cloud over 3 sites, 3 nearby AA sites. And this is called, one of the groups have dubbed this fidget spinner. And the reason why you end up with a fidget spinner is because you cannot localize in a triangular lattice when 2 valleys have opposite valley churn number. The issues, even when you vanillarize to this fidget spinner shape, all 3 groups had to sacrifice something. And the sacrifice that had to be made was that not all the symmetries could be retained. So for instance, in this paper, Koshino and others, they had U1 valley symmetry, but C6 rotational symmetry was only approximate. Kang and Vafek had approximate C6 rotation and approximate U1 valley, and Po et al. Had explicit C6 rotation, but they had to be compromising the U1 valley symmetry. And the fact that you cannot have even this extended van der orbital, which is a pretty difficult object to work with, respecting all the symmetries, made all of these groups generally kind of turn away from local picture and try to focus on the momentum space picture. But not being able to hold all the symmetry is okay if you're looking at BN aligned twisted bilayer graphene, where the BN layer explicitly breaks the symmetry. So that's what we want to focus on, and we want to think about this. We want to take this extended shape of the van der orbital on the face value seriously and see what the consequences are. The first thing you can notice is that the fact that the single electron is extended over this 3 sites means you cannot ignore further range interaction. Normally, if you have exponentially localized van der orbital, people often feel invited to think about, say, Hubbard model, where you only consider, extremely local interaction, where you say, okay, I'm going to care when 2 electrons are on top of each other, and I'm not going to care when they're not on top of each other, even if they're 1 lattice apart, 2 lattice apart. Now that I've got my electrons spread over with 3 arms or 3 lobes, spread over 3 lobes, if I have 2 electrons on top of each other, that would be overlapping exactly at the center of the van der orbital, one and the other both at this A, B site, and then 3 lobes will be overlapping. But even if I don't do that, if I try to, in the presence of 1 electron here, if I try to put another electron on this BA site, I would have 2 lobes overlapping. And if I try to put electron further away at this AB site, I would have 1 lobe overlapping. So this is a cartoon of further where the range of interactions that are contact-like, how far they extend. So right on top of each other, obviously the interaction strength will be the greatest, but you go out of a few steps, you still have significant interaction strength because you're still overlapping several lobes, multiple lobes are being overlapped. So this is an explicit calculation, and the numbers depend on your choice of linearization that various choices you make in doing DFT or ab initio studies. But we wanted to take a simple limit based and just focus on the geometric aspect of this problem. So what we are going to think about is that the Vannier centers live on a honeycomb lattice, A, B, BA. There are 2 sites on a honeycomb lattice. And a third of electron occupy the dual triangular lattice. And this is a problem where, once you have these extended Vannier orbitals, not only your interactions are further range, your hopping also becomes more complicated. And there's a rich interplay between hopping and interaction. But we can arrive at a very simple picture if we focus on densities that are density of 1/3. So we're going to focus on density of 1/3 and really just limit ourselves to these interactions that are actually contact interactions where 1 or more lobes are overlapping. So once I get to that point, I can replace my Vannier orbitals with actual fidget spinners here. It was a thing that elementary school kids really liked a couple of years ago. Maybe it's not so much in the fashion anymore, but this is what a fidget spinner is. The center has an axle and the thing spins, and somehow this was what the kids were all the rage about. Now my Vannier orbital has a fidget spinner shape. So once I place 1 electron, I can start to place other electrons, which are my fidget spinners. And the rule of the game from the interaction is that I don't want any lobe to overlap. So here is one way to place the next fidget spinner. And then another one. And now you see the problem of thinking about the effective interaction became the question of tiling my system with these fidget spinners. Why? At 1/3 filling, I can afford to do this. I don't have to ever overlap. I can just tile, and that would be the best I can do for the interaction energy perspective, from the interaction energy perspective. Once you start playing with this, you immediately recognize that the way of tiling is not unique. First of all, the fact that I am tiling these fidget spinners, and that I am making the energy cost of overlapping orbitals the biggest scale in the problem means that I have an incompressible state at 1/3 filling. So I get incompressible state like almost free. Like I didn't have to do any work to get an incompressible state. But what we are interested in is to understand the nature of this incompressible state. Is it like a Wigner crystal, or is it like a charge density wave, or is there something more to it? So the first observation that came to us hinting that there is something very rich about this problem was the following observation. So on the left, this is one tiling pattern that we made with 3 fidget spinners. But I could have placed my second fidget this way. Then I arrive at a different tiling pattern. So after trying a couple of different tiling, we realized that there are quite many different ways of tiling. When all of these tiling are the classical ground state, strong coupling limit ground state of the problem, because I only have interaction energy, and these are all patterns that are not costing any interaction energy. This is a zero energy state. But there are many choices that I can have. You can observe here, this is A, B, B, A, B, A. Here, A, B, A, B, A, B, A, B. So different tiling patterns have to do with whether I'm choosing A, B, or B, A. That's underneath our degeneracy. But once you start to find that there are several different patterns, this is a ground state. So we have a ground state degeneracy, right? And when it is not one or two, but there seems to be many, you realize this is sort of a mathematical problem. And that brought me back memory of this time in 2015. That's my son, when we were visiting Museum of Math. They have these tiles and this tessellation wall. That's where I became, for the first time, interested in tiling. And then I had forgotten about it altogether until we started working on this project. One thing I did learn when we were playing with these monkey tiles was that there are many ways to tile. So if we have a reason to believe that there are many ways to tile because we tried counting a couple, after finding 1, 2, 3, we realized that, likely there are many, and counting one at a time is not going to be a winning strategy. Fortunately, in the StatMed community, people have thought a lot about tiling problems. And these authors in 2001 have studied the identical problem because in the strong coupling limit, I have a classical problem, and they have solved this classical problem. They found that the model that we have derived from twisted bilayer graphene at 1/3 filling has extensive ground state entropy, and they calculated it using beta ansatz. So that allowed us to make a connection and declare, hey, we have a ground state with extensive degeneracy. Now, that extensive degeneracy is a result of this model that we've considered, and perturbations, including further range interactions that are range is further than what we are considering, that is contact, or effects of quantum fluctuation is going to lift that degeneracy. So now there's a question of that there is a reason to study how this degeneracy will be lifted. The different degenerate states are all incompressible, but with uniform charge distribution. Uniform as long as we say that the charges are really equally spread out over the 3 lobes. Every AA site will host 1/3 of a charge lobe, because whether I have a center here or center here or center here or here or here or here, I have 1/3 of a lobe at this AA site. So we have this covering of uniform charge distribution. Now, however, if we think about just the center of the Van orbitals, not all A, B, and BA are being occupied. So if I just focus on the center of the Van orbital, it is a problem that is reminiscent of Wigner crystal problem. And I'm going to have a charge order at 1/3 filling. And the charge order can be thought in terms of these phases. Now, there are 3 upward facing or AB centered lobes, and these 3 are downward facing or BA centered. So this is the result from these authors calculating entropy using using beta ansatz. But even if you do not walk through that exact solution, you can see why there is entropy, because if I start from one configuration of everybody polarized to be A, B, or BA, I cannot make a single flip, but I can make a flip line where I flip every single orbital from upward facing to downward facing. And those flip lines can only meet at 120-degree angle, forming a generalized hexagonal arrangement, and these hexagons can breed. So this kind of thinking up into the extensive entropy was something that people thought a lot about in studying melting, 2D melting way back. And that's the same mechanism for giving us extensive entropy. And we can see that extensive entropy is, even if we introduce further range interaction that breaks that degeneracy, the entropy remains large up beyond the temperature scale. So with the further range interaction, the ground state becomes non-degenerate, but entropy quickly rises. And that is an interesting observation from experimental perspective. So now we want to look at how the degeneracy can be lifted. So no touching condition, where we don't want any of the lobes touching, can be thought in terms of cluster charging energy. In other words, if I have one of these 6 triangles occupied, I don't want any of the remaining triangles occupied. That is from the perspective of the Vannier centers, which are A, B, and BA, forming an hexagonal lattice. It is to say, in this hexagon, I want the total charge to be 1. And so that's my cluster charging term in the Hamiltonian. Degeneracy will be lifted if I introduce the first neighbor interaction that goes beyond this hexagon. And there are 2 mechanisms that can give opposite signs for the fourth neighbor interaction. One is Coulomb interaction, which would give positive sign to the further range interaction. And that is going to favor this kind of arrangement where AB or BA is polarized. You can also see that this state would be ferroelectric because there's more charge at the bottom than at the top. And from the Vannier center point of view, this is a familiar √3/√3 state. However, we're dealing with electrons with spin and direct exchange, which favors electrons being nearby so that they can because then they can be ferromagnetic through exchange interaction. Direct exchange term would effectively make the sign negative, and that would favor this kind of arrangement from the Vannier center point of view, and this is the Vannier orbital point of view. You can see that this state in the negative U4 case is rotational symmetry breaking state, because there is sort of a flattening, squishing of the lattice, and there is sort of a quasi one-dimensional nature to it. So these 2 states, √3/√3 or brick wall, will be selected in the limit of 0 kinetic energy. In the extreme strong coupling limit, one of these two will be selected. And brick wall, √3/√3 does not have ground state degeneracy other than 3 associated related by phase shifting of the registry, but the brick wall state has sub-extensive degeneracy that is linear. Now, the next question is, from these ground states, what kind of excitations can we have? Given that we are looking at fractional state, can we have fractionally charged excitations? Can they be interesting? And another thing that will be interesting is to find out what would be the role of quantum fluctuation. So let's look at excitations from a √3/√3 state. This was Dan's observation. Dan realized that, well, you can make first of all, you can make a charge excitation or take away charge, not necessarily in units of full electron, but you can take away charge in units of 1/3, which is plausible given that we have electron kind of spread out over 3 sites. And you can see this explicitly, that if you make an arrangement of orbitals in this fashion, and you use the polarization and integrate the polarization around the loop to assess the charge localized in this region, that comes out to be 1/3. So this is a 1/3 charged object. However, this 1/3 charged object here cannot move, because if I try to move this over there, in order to move this 1/3 hole to this site, I have to flip this orbital over here, but that's going to violate the no touching condition. So this is a 1/3 charge that is totally localized and immobile. And this seems to be reminiscent of fractons, or where that in the sense that these are immobile objects. There is no anti-vortex, but they three of these fractons would trivialize. They form a vacuum because three of them would form a full electron. Now, there is no anti-vortex because if I just swap every single orbital around, this is a totally allowed move. Locally, this looks as if I formed the anti-vortex, but I didn't change the global texture. So these are not vortices, and there is no time reversal symmetry breaking. Nevertheless, they are 1/3 charged fractional objects. Another type of excitation one can think of is some object that has 1/3 charge and that can only move along a line. So here I have created a hole where I removed the full electron because I have taken the whole triangle and removed it. But you can see by moving other orbitals, I can move 1/3 of this hole along a line. But their movement is restricted to be one-dimensional. So these second type of excitations, starting from a full electron, 1/3 piece can each move along 3 directions, and leaving behind a wake of flipped orbitals. But around this region, there is a 1/3 charge. This is sort of reminiscent of solitons in Sushri-Verheger chain. Ferromagnetic brick wall state also has a fractionally charged object. This is how 1/3 charge in brick wall state moves, and it moves along a one-dimensional line. It cannot move across the line, so this is also one-dimensional. This brick wall state has sub-extensive entropy because each line you can choose, so this line can be squished in one direction or the other. So there is a twofold degeneracy associated with each line. So the linear dimension of this linear dimension of the system would give me the degeneracy. So observations of this the restricted mobility made us think about the nature of these fractionalized objects more carefully. And we started to wonder, are they a version of fracton? Fracton, this is a Wikipedia page about fracton. Fractons are immobile objects in isolation. When they bunch up, multiples of fractons can move around. And that's kind of like our 1/3 charge. 3 of them forms an electron and they can move around, but individually their movement is restricted. All the previous considerations of fractons focused on 3-dimensional systems, and none of them are really realized. Although there were insightful connections made with lattice defects. So the Raziovsky and others have made the mapping between fractons and lattice defects, where the disclination is an immobile object, and this location can move only along one direction because there's a dipolar nature to it. Our fractional objects also have we have immobile object and linearly moving object. So we can now compare, sort of summarize what we know about our fractional excitations. In root 3 by root 3 state, the ground state degeneracy is just log of 6, the 6 different registries. It respects C3 symmetry, and there is a fracton in the sense of 1/3 charged excitation that cannot move, and linon in the sense of 1/3 charged object that can move only along one direction. The brick wall state breaks C3 rotational symmetry. It is a nematic state, and it has residual ground state degeneracy, which has to do with this coupled nature, this 1D kind of reduction that we can look at. And that 1D reduction also is responsible for restricted mobility along the line. These are observations. We're making sort of phenomenological observations of the theoretical object that we found. And to really understand whether we can think of them as fractons, we need to, we need to have a full theory, perhaps understanding the hair rank gauge theory perspective. And that's something that we are still trying to understand. But nevertheless, given how fractons have never been realized, having these aspects of fractons, being able to realize it in an experimental system would be very interesting. Now, what about the effect of quantum fluctuation going up in the hopping direction? So if you want to understand what quantum fluctuation can do, when you have extensive degeneracy, what we want to find are different configurations that can connect with local-ish moves. Let's say in like quantum dimer model kind of perspective, where whether you can form resonance that can connect different degenerate ground state and take advantage of it. That will be a way for the order out of disorder can work. So we need to identify local moves and configurations that can connect without violating the conditions that's giving us the ground state. And that got us to recognize the smallest local unit we can form is this shape. And that has this double ring kind of structure. If you can see this. So here we are showing what the resonance will look like. This going to this, this flipping, this orbital flipping. It's a hopping, right? This orbital flipping this way, this orbital flipping that way. These are, so these movements would form a smallest unit that can resonate. And it looks like a double ring, the infinity symbol. Apparently, there's a word for this symbol called lemniscate. So we're calling this lemniscate liquid, the resonating state. There is soup, Korean soup, where you make these little rice blobs that also has this shape. And I thought that was kind of cute. It's also in a liquid state. All right, so quantum order by disorder, we want to recognize the smallest unit. So we start by trying to see whether we can form a resonating state with, the smallest pieces we can have. Now, this kind of move of flipping this triangle over here, this over there would not work because those triangles cannot be all simultaneously occupied. They violate the no touching condition. So neither of these operators are allowed to be operating in the ground state. So now we build up from these moves. Now we take those and make a larger unit. And now these triangles can legally be resonating, but what this leaves out is the center, which should be occupied. This introduces a hole. So this cannot be also, this once again cannot be the description of a local resonating move. And that takes us to this L2 operator or lemniscate operator, where if I take every minus and 2 plus, that is a move. Then we can resonate between minus and plus, and that is a move that is allowed connecting two different configurations that are in the ground state manifold. So now that we have identified the resonating unit, we can think of the full effective Hamiltonian where we focus on the cluster charging term as the largest scale, but considered quantum fluctuations specifically in the form of the resonance of the lemniscate, and ask what the further range interaction can also do. So this model, now we can take it to a solvable limit of RK-like point by introducing an on-site, so-called dimer on-site kind of term. And now this is a Hamiltonian where we allow for hopping between sites. So this Sj of x is a hopping operator, creating and annihilating fermions. But we only allow these hoppings as long as the system is respecting the cluster charging constraint, so that every minus site will be losing an electron and every plus site will be gaining an electron. So this projector acting in front of this hopping term and the on-site term defines a model that is like a dimer model. And we can focus on the RK point where it is explicitly solvable. And that would be looking at these kind of resonance moves as dominant effect of kinetic energy. Now, to gain further insight about the fractionalization in this quantum lemniscate liquid, we follow the steps taken by Balance, Fisher, and Gervin in this paper, where they studied easy access Kegome antiferromagnet. Just like the problem they studied on a Kegome lattice, we have a problem starting with a honeycomb lattice, because if I look at the centers of the van orbitals, they live on honeycomb lattice. So their solution was to dualize the model and approach it from the dual side, and we can take the similar steps. Dual lattice of honeycomb lattice is a triangular lattice. So now we're back to the original triangular lattice. But instead of looking at this as a plain triangular lattice, it is productive to think of this triangular lattice as 3 interpenetrating hexagons. But then we can readily form fluxes associated with these green hexagons and blue hexagons and red hexagons. If I put Ising degree of freedom on each of the bonds, I have 3 types of Z2 gauge fields: red, blue, and green. But because every site has two of the this red type and blue type coming together at a given site, they are not independent. So what in the first site looks like Z2 cross Z2 cross Z2, that is 3 flavors of Z2. Ultimately, this is just Z2 cross Z2 because they're not all independent. SZ operator, which was the counting of the electron at a given site, can be written as a product of 3 M particles. So SZ operator, putting a particle here, for instance, right here, would be violating 3 bonds associated with 3 plaquettes. And that's why violating 1 blue bond, 1 green bond, 1 red bond would give me a product of MR, MG, MB. And that's a local operator. So there is a constraint that MR, MG, MB has to be trivial, which is another way to look at how this is not Z2 cross Z2 cross Z2. Now in this dual lattice, the SZ operator, which is creating an electron, it can be thought of as SZ operator here, can be thought of as a product of the sigma x's on the 3 bonds surrounding. So these 3 bonds. And the cluster charging term amounts to giving me a Gauss law condition. So now I have Gauss law for the red bonds, Gauss law for the blue bonds, and Gauss law for the green bonds. Hitting a particle here, electron here, fermion here, violates the Gauss laws for each of the 3 bonds, 3 plaquettes. SX operator can be associated with this bond of sigma z's. And so this is SX operator, 3 bonds of sigma z's. And this bond violates this Gauss law condition. And this bond, vertex violates blue Gauss law condition. And this vertex violates this 2 Gauss law conditions. So this violates blue and red. This site violates blue and green. This site violates red and green. Using this dual mapping, we can recognize at the RK point that visons are going to be gapped and there are deconfined spin-ons. And we can now come back to the perspective of the original problem and think about the fractionalization, fractional charge from original electron charge from 2 different perspectives. One is the single fermion violates 3 plaquette constraints. These 3 plaquette constraints These are the plaquettes whose centers are AA sites, formed by ABBA sites. That is the original perspective. We can now think of also this single fermion as creating 3 M particles. So in that sense, these M particles are as if they are related to original electron charge of a third. But if we, and this would be a way of understanding how to think about the melting, because the melting that takes us from these 2 crystalline state to this quantum lemniscate liquid will have to be through these fractional objects, which are fractionally charged fracton-like objects from the strong coupling limit. From the quantum lemniscate liquid side, they appear to be anyons, these E and M particles. We don't yet have a theory that connects the two, how we melt, and what are the roles of the fractons in melting and taking us into a quantum lemniscate liquid. That is something that we are working on right now. And despite this not being all worked out, I thought I would present this to this audience because I thought maybe some of you would have ideas or interest in helping us out. But moreover, I think it is really interesting that these states might be underlying the experimental observations, and it might be possible to detect the fractional charge without magnetic field in this fractional filling Moray systems. So how would we detect that? Well, I showed you earlier that the STM image of this Moray system looks like this. Every AA site has some intensity, and they all look about the same, and they're all equally intense. The defect, that's the fractional charged object that we are after, is going to appear like a defect. It's going to appear like just one AA site missing. And that defect would have 1/3 of a charge, because at 1/3 filling, you need to be removing 3 sites to be getting a full charge of electron. So this is what we would like experimentalists to look for. Because there are different phases here, one might wonder, like, how do you control which phase you're in? This phase, √3 phase, has net electric polarization. So there is ferroelectricity in this phase. This phase has magnetism, that this is a ferromagnetic phase. So applying external fields such as electric field or magnetic field might be a way to put the system into this specific strong coupling phase, and then one can start looking for the fracton-like objects. To summarize, I talked about how the 1/3 or fractionally filled TBG Moray could be a very unique and novel playground for new types of fractionalized objects, excitations. And we are interested in developing our observations further through collaborations with experimentalists looking for these fracton-like objects, and through collaboration with theorists, further developing the understanding of what's, they are like, they wag like fractons and they bark like fractons. Are they really fractons? Like, we would like to understand that better. And we would very much like to start understanding how to think about the transition between these phases. With that, thank you for your attention.
Thank you. So the talk is open to questions now. The claim is that this quantum lemniscate liquid is a Z2 gauge theory. But you seemed a bit uncertain. So doubt there, or this is firm? And,
No, I don't. Yeah, we don't have doubt about Z2 cross Z2 gauge theory structure of the liquid phase itself. What we don't quite understand is how to connect So in the gauge theory side, we have 3 E particles and 3 M particles, and they are anyons, like in Kitaev model. But what we don't yet know how to connect is those anyons. Those are also a type of fractional objects, right? We don't know how to connect those anyons to the fractons of the strong coupling limit. So we understand this limit of strong coupling limit. We understand this limit. We don't know how to cross between the two phases. That's one thing that we don't understand. But the description of quantum lemniscate liquid as a Z2 cross Z2 gauge theory is really, you can follow the same steps as Balance, Gervin, and Fisher, and there isn't anything unclear about that.
The Balance, Gervin, Kagome model, people have added various perturbations to that and studied quantum phase transitions, which could be exotic, like XY star, in a rather controlled way. So how about playing that game?
That would be right. That could be something that can be done, right? That would be one direction of asking what happens to this quantum lemniscate liquid, and that is in a way adding another axis out of the plane, right? So if you want to add additional terms that are not this, which will just break the symmetry and give me a crystalline. These are 2 crystalline phases. And if you add other terms, that can take me out to another direction, another dimension, and there will be quantum phase transitions.
But even the U4, so the question is, is there a sign problem?
Oh, can this be simulated? Is that a question?
Yeah, exactly. Just with T and U4, so just fixing T and increasing U4
I don't
positive or
know.
negative.
Yeah. Well, this T is should be actually T tilde, just keeping the resonance term, right? If you only keep the resonance term and you take it to the RK point, you can just solve it. So that's what we've done. This is very frustrated, so I doubt it can be simulated. But we haven't tried to push that all that far.
But I guess, yeah, it doesn't prevent you from looking at theoretical, like field theory descriptions where you condense.
Yes, it does not. No, not
but,
at all. Yeah, that would be interesting to look at.
And regarding the fracton-like excitations on both sides, so when T is 0, these are fairly simple classical objects. You can understand the mobility from the constraints. But you're saying that these are gap states, right? So turning on a small T there wouldn't, break this fracton structure.
Yeah. Right.
So that you would say is robust even to quantum fluctuations?
To a degree, yes. Right.
Of course, if it's too large, then God knows. And in fact, you can transit into this QLL state. But because these fractons look like very classical objects. So I don't know if people in that literature distinguish classical from more quantum-like excitations, or is it all the same and it's like dislocations and you call that
also
fractons?
the thinking in terms of dislocations is this mapping that there's a picture of this mapping that you can make. The issue was the reason why this didn't get to everybody saying, okay, I have fractons on my crystal, was because the lattice defects are completely immobile by definition. So there is no dynamics. You cannot give them any dynamics. You cannot take any quantum limit. But the same cluster charging constraint that gives us fractons also allows for the resonance. So in our problem, dynamics is not forbidden by from the outset. You know, it's not like a classical solid with a lattice defect. And the dynamics, this resonance move is dynamics that is allowed, preserving the cluster charging.
Mhm.
So it's different from the lattice defect perspective. But there seems to be some connection. So one way we would like, one direction to pursue would be to take, so in this lattice defect considerations did not include the melting, what happens near melting. These are, you know, sort of very crystalline states. And maybe thinking about melting might be a helpful way to pursue understanding that our melting that we want to understand. These are sort of speculative thoughts we have at the moment.
And
I
the
don't know
ex-
whether that's an answer, but you know,
yeah, yeah, yeah.
we're actively thinking about this. And
Mhm.
really the reason why I'm giving a talk on this when it's far from complete. Although we will be publishing this level of understanding very soon, is because I want to invite bright people to help us out.
And the transitions, the melting of this liquid,
Mhm.
or I should say crystallization of
Mhm.
this liquid, do you expect this to be critical, or there's arguments that would say it's first order? What's your, do you have any
I
intuition
have
about
no
the
idea.
transition?
I have no idea. I don't know how to make it melt yet. So I know it has to melt, but I don't know how to make it melt. So I have no idea.
Some numerics at some point would also be interesting. I mean,
Yeah, some numerics or maybe some field theory with the right
both.
starting point. Yeah. Mhm.
Yeah, so I have one question in the audience. You have, yeah, okay, just talk into the computer.
Hello.
Actually, maybe
Okay.
it's a bit simpler.
So I have a question about the fracton.
Mhm.
So I think in like a fractal, the theory, they have the charge conservation stuff or dipole conservation. So I
Mhm.
wonder if we have the similar conservation
Right. So
laws.
we have trimer conservation, dimer, not dipole, but we have three tripole conservation because three fractons make an electron. So each fracton carries 1/3 electric charge. And once when they are bound into a full electron, they can move around.
Okay, then in this sense, the full electron is their dipole.
Full electron is their tripole. Yeah.
Their tripole.
Mm-hmm.
Okay.
Maybe I can ask another question just about experiments that distinguish these three different phases.
Mm-hmm.
Because in experiments, they see some incompressible state.
Mm-hmm.
You briefly went over maybe some possible experiments. So what's
Mm-hmm.
what should be measured to determine whether it's break this root 3, or even a more interesting?
Yeah. So rotational symmetry breaking has been observed. It's hard to know from observation of rotational symmetry breaking whether it is this specific state, but this state is ferromagnetic. So there is spin polarization. This state, √3/√3 state, has electric polarization. You see this triangle is pointing upward. There is, and you know, there is more charge at the bottom than at the top, right? The distribution of charge is not rotationally symmetric. So there is net polarization in one direction. That would be, so observing ferroelectric effect would be a way to know that you have a √3/√3 state. Or conversely, you can apply electric field to align your system into √3/√3 state, and then look for this kind of defect.
Is that something that's underway, these experiments, or? Is it something
Is
that
that
people are
a way?
trying to?
Yeah. So the kind of experiment that could detect this would be scanning single electron transistor. What's his name at Weizmann? The name's not coming to me. He has scanning single electron transistor with a resolution that is approaching, this scale. So Shahal Ilani, Shahal is interested in looking for this. One could also look for this with STM. Nobody has declared that they found it, but we're starting to look for them.
But you say that at least they've seen rotational symmetry breaking.
Right, the rotational symmetry breaking was observed by transport in the. So I showed Pablo's data at some point early on. Sorry, I'm doing what I hate other people doing to me. But if I escape, I have to reshare and stuff. So there it is. So this above superconducting dome, this region is known to be rotational symmetry breaking, anisotropic. But whether that is because of our brick wall state is hard to know. But if we have an incompressible state that breaks rotational symmetry, because the line on moves only along one direction. So that's a very anisotropic transport, right? When you dope lightly, so incompressible state is right at 1/3 filling. Now you dope it a little bit, then you'll be introducing these line-ons and fractons. And the line-on, where did it go? This line-on moves only along the wire, right? Along this direction. So if you're in this state and if you doped a little bit and got a line-on, your transport will be very anisotropic because there will be charge movement along this direction, no charge movement along that direction. So that would be an indirect signature, finding anisotropic transport, doping slightly away from the incompressible states right at 1/3 filling.
Would that be compressible along one direction, or
Yes, it'll be compressible along one direction, yes.
whereas they see activation along all directions in the
They see activation along all directions right at 1/3 filling. You have to go away a little bit. And in the experimental systems that are available right now, most likely you have domains. If you have nematicity here, there are 3 directions of nematicity. It's a discrete symmetry breaking. So there will be domains.
Yeah.
So that will have to be aligned to see macroscopic effect.
Mm-hmm. It's interesting. Let's hope the experiments happen so we can ponder more. That's all we have for now. So let's thank again, Eun-Ah, for a great talk.
Thank you.